Done?
Yes, sir.
So make a note of it. So with this, the main context of this chapter is over. There is nothing else that can be asked. Okay, we did problems also. Okay. So as I told you, this damped simple harmonic oscillations, they will not ask you. Okay, they cannot actually ask because all these expressions are given without a reason. It is not easy for you to remember also because all these are not there even for 12th standard. So I will just give you an outline of what is the meaning of damped. Okay, damped simple harmonic oscillation means. Do you guys know what is the meaning of damped? See, if suppose I take a simple pendulum, I take it to this position and release. Okay, I take it to this position and release it. Let me call this distance as amplitude, or I will call this theta as the angular amplitude. It is a maximum angular displacement that is possible. Once I release this, what will happen is the pendulum will come on the other side to the same angle theta, right? Again, mg sin theta will start acting in this direction and it will go to the other side. And let's say it is again going back to the same value theta on the other side, here also mg sin theta. Now my question is this the way the pendulum is going to oscillate throughout? So will it be able to cover these angular displacements theta throughout its journey? Or will there be a decrease in the value that is going to take place? Guys, are you able to understand my question? I'm saying, is this simple pendulum going to be in oscillation throughout its life? Like let's say you're coming, you have put this in oscillation, let's say you're coming after 1 hour. If you look at it, do you think it is still going to oscillate?
No, sir.
Why? What will happen?
Theta will reduce to 0, sir.
Theta will reduce to 0 and there will be a particular point where
Restoring force will also be 0.
Where the value of theta will become 0 after a particular point, means it will exactly come to its equilibrium position and stop. Right? There will be a particular position where there will be a particular time, let's say after 2 hours, it will come and stop like this. It will be still. It will not be oscillating anymore, right? So in the 2 hours process, what exactly has happened to it is, what has happened to it? Its amplitude has got damped. So damping means what? The decrease in amplitude, and the decrease in amplitude will obviously happen because of whom? Because of a resistive force acting on the system, and that resistive force is what is given here. This is the only thing you can know. Guys, are you able to understand? So to put it in simple terms, if you want to understand what is the meaning of damping, what is it? Damping means decrease in amplitude of any oscillation. That's it. So next time onwards, if I ask you what is the meaning of damping, you just need to use the word amplitude and decrease in its value. That's it. Okay.
I have a
similar.
So this damping is used only for oscillations, sir? Like in case of
Oscillation, see,
pendulum alone.
okay, if you want me to give a more specific example, let's say you're here, okay, your friend is here, okay, you speak to him with a particular volume, okay, you're not shouting, you're just talking to him normally. Let's say the distance between you both is x. If your friend, let's say he goes few meters away and he stands here, do you think if you try to speak with the same intensity in the sense same amount of volume, do you think your voice will be able to reach him as clearly as it happened at this point?
No, sir.
Okay, why is it happening?
It's distance increase. It's no longer
Distance
x.
is increasing and there is a lot of absorption taking place in the medium. And if you want me to answer the same question technically, I will say the amplitude of your voice, that is the loudness of your voice, has got damped. Okay, so what you need to do for your voice to reach him, you definitely need to start shouting. Shouting means you're increasing your loudness. Increasing your loudness means increasing your amplitude. So damping has something to do with which parameter? You tell me now.
Amplitude.
Amplitude of anything. It can be an oscillation or it can be a wave.
Okay, sir. I understood.
Got
Thank
it?
you, sir.
Yeah. So since it is given in this chapter, I'm just trying to explain with the context of oscillation. But damping can be anywhere. See, for example, we use communication system. Why do we use a mobile phone to speak for a person from here to somewhere else? Well, your voice obviously can't travel, no? If you want to speak somewhere to someone in the, let's say in the next state, you have to either shout or even sometimes even if you shout, your voice will not reach, right? Because there is something called as damping happening, right?
Yes.
So major application of this damping will actually take place in communication systems. Okay, here they have spoken in terms of damped simple harmonic motion, just to bring in all these second degree equations. These are all called as differential equations, which obviously I cannot explain it now because you'll get confused. If at all they explain it in your school, you let me know. I will give you the outline. That's it. Okay, if I do all these things, you will unnecessarily get confused. This graph I will explain if you want. See, initially there is an amplitude existing. Amplitude means distance from the bottom to this portion. As the amplitude keeps decreasing with time, this kind of a motion is what is called as damping. So damping goes on increasing successively from the curve A to D. That's the meaning. Okay. If you know this, this is more than sufficient. Similarly, forced oscillation and resonance will make more sense in the next chapter. That time I'll explain. Okay. Resonance concept will make more sense in the next chapter. I'll explain it there. So with this chapter is over. Is there any other doubt that you people have? Any other concept that is not clear?
No, sir.
Okay. See, since this chapter is important, okay, so today is Wednesday, right? Thursday, Friday, Saturday, Sunday. Okay. See, these